Welcome to this explainer, where we're going to completely puncture the surface level hype around repurposing old EV batteries for stationary storage. I mean, on paper, it sounds like an absolute universal win, right? Take depleted car batteries, give them a second life on the grid. But as we're going to see, the gap between boardroom theory and actual on-the-ground practice is, well, it's massive. Let's break down the severe technical hurdles that turn this really hopeful narrative into a pretty gritty reality.
Because honestly, deploying these retired batteries without a fundamental grasp of those extreme technical hurdles, it literally turns standard asset management into a high-stakes game of roulette. And no, that's not an exaggeration. We aren't just plugging recycled AA batteries into a TV remote here. We're talking about massive utility-scale applications where a single operational blind spot can trigger some truly catastrophic financial and physical consequences.
So, let's start with part one, the sustainability hype.
There's a severe disconnect here that we really need to talk about. If you look at a typical corporate sustainability deck, Second Life batteries are the ultimate buzzword. They're pitched as the absolute pinnacle of the circular economy, totally eco-friendly, and wrapped up in massive initial cost savings. But step onto the actual shop floor, and the operational reality hits you like a ton of bricks. System engineers are dealing with extreme cell degradation and wildly varying internal resistance. Suddenly, that eco-friendly promise morphs into a ticking clock. Which brings us right into section 2, the shop floor reality. Just imagine the scene for a second. You're racking up thousands of retired automotive cells into a giant utility-scale container. Now, because these batteries have lived completely different first lives, maybe one was driven through freezing winters, another baked in desert summers, some were supercharged every day, others barely depleted, combining them is a monumental headache. Without hyper-precise sorting, you've essentially just built a Frankenstein's monster of energy storage. The extreme heterogeneity or variance in cell degradation literally becomes a ticking clock. It's not a matter of if issues will pop up, but exactly when.
Okay, let's look at section 3, the weakest link problem.
The core culprit behind all of this is cell heterogeneity. And we aren't just talking about a slight difference in remaining battery juice here. We're looking at extreme variance across 3 critical metrics: overall degradation, energy capacity, and internal resistance. Basically, every single cell comes out of its first life with a completely unique chemical fingerprint. And it's exactly this heterogeneity that transforms a really promising circular economy asset into a massive operational liability.
If we break down these specific operational risks, it's pretty easy to see how they practically guarantee accelerated degradation. When you mix batches, the internal resistance varies wildly, which creates brutal inefficiencies and excess heat. Then you have capacity fade, which leads to extreme mismatches, meaning some cells fill up way too quickly while others lag dangerously behind. And most critically, the thermal limits become entirely unpredictable. You completely lose your standardized safety threshold, which leaves you managing a highly volatile utility-scale patchwork.
This right here brings us to the absolute core of the issue. Your massive multi-million-dollar battery string, it's only as strong as its absolute most degraded individual cell. Because these systems are strung together in series, the weakest link dictates the whole shebang. If just one cell hits its maximum capacity or its thermal safety limit, the entire string has to be throttled back or completely shut down. I mean, 99 perfectly healthy cells simply do not matter if one highly degraded cell bottlenecks the entire container.
And the downstream effects of ignoring this basic physics reality are absolutely brutal. If asset managers just rack these things up and ignore the mismatch, a massive domino effect takes hold. First, you get accelerated degradation, mostly because the healthy cells are working overtime to overcompensate for the weak ones. Then, you get premature system failure. And remember those beautiful, massive initial cost savings that looked so amazing in the boardroom? Yeah, those get completely wiped out by downtime, maintenance nightmares, and inevitable replacement costs.
So, how do we fix this? That's section 4, strategies for commercial viability.
It is actually possible to make Second Life projects commercially viable, but let me be clear. It requires a rigorous, zero-compromise playbook. Step 1. You need hyper-precise cell sorting before anything gets racked together. You have to know the exact health of every single unit. Step 2. You must actively group those cells to address resistance and capacity mismatch so they actually play nicely together. And step 3, you have to engineer overarching system controls specifically for thermal limit variance, just to ensure localized hotspots don't trigger cascading failures. We're talking about incredibly intense, meticulous engineering.
Which ultimately leaves the energy storage industry with one final, very high stakes question. Look, we know the corporate promise is super alluring, but given the actual shop floor reality, does the massive overhead required for all this hyper precise sorting actually outweigh the initial economic benefit of using retired batteries in the first place? It's a razor thin balance between sustainability and operational reality. And honestly, how we answer that question is going to completely define the future of the circular battery economy.